Hi, in this video we are going to talk about a concrete example for the dijkstra shortest path algorithm. So as we have discussed in the source code section, first we have to initialize all the vertices in the graph. And in this situation the starting vertex will be the vertex A, so the distance is going to be set to 0. And all the other minimum distances for other vertices in the graph is initialized to be infinity. Of course, we have several directed edges. These edges will have some weights, for example 5, 15, 3, 9 and so on. So in this graph we would like to find the shortest path from the vertex A to vertex G, and we would like to construct the shortest path tree that's going to yield all the shortest paths from the starting vertex to all the other vertices. So we start from vertex A. We consider all the neighbors. A has the neighbors B, H and E. It takes 5 units to get from A to B. It takes 8 units to get from A to H because the edge weight is 8, and it takes 9 units to get from A to E because the edge weight is 9. Okay, so for node B we have to decide what is smaller, 0 plus 1. Why 0? Because the starting vertex has the minimum distance 0 and the edge weight is 5. So what's the greater, 0 plus 5 or infinity? Because the minimum distance for vertex B is initialized to be infinity. 5 is smaller, so we have to update the minimum distance for node B, plus we have to track predecessor when we update. Okay, if we do not update, then we do not have to update the predecessors as well. In this situation we updated the minimum distance for vertex B to 5, and we tracked that, okay, we came from the vertex A. What about the node H? We have to decide what's greater, 0 plus 8 or infinity. And because 8 is smaller, so we have to update it. So that's why the infinity has been updated to 8. What does it mean? That it takes 8 units to get from the starting vertex to the edge. Okay, we haven't considered all the possibilities, but so far this is the best solution. What about the E? We have to decide 0 plus 9 or infinity. Of course 9 is smaller, so we update it. In this situation the heap content will be B, H and E. So we have 3 vertices on the heap. The B has the minimum distance 5, H has the minimum distance 8 and E has the minimum distance 9. We have to take the minimum, so the B. We have to make the decision according to the minimum distance. So we know that 5 is the smaller out of 8, 9 and 5, so that's why we are going to visit the node B. And of course we remove it from the queue and we set the vertex A to be visited, so we are not going to consider it anymore. We are standing at the B and we visit all of its neighbors, the D, the C and the H. We pose the question that for the node D, for example, what's the smaller, 5 plus 15 or infinity? Why 5 plus 15? Because we know that it takes 5 units to get to B and another 15 units to get from B to D. So that's why the overall cost going from A to D will be 20. 20 is smaller than infinity, so we update it and we update the predecessor. So the predecessor of D will be the B. Okay, for the node C we have to decide that what's smaller, 5 plus 12. Why? Because 5 is the minimum distance to get to B. And it takes another 12 units to get from B to C. So that's why 17 is smaller than infinity, so we have to update it, and we have to update the predecessor of C pointing to B. Okay, then what about the H? We have to decide whether 5 plus 9 is smaller than 8. It's not greater, so we do not modify the minimum distance for H as well as that we do not modify the predecessor. Because in this situation we know that the shortest path from A to H is to go directly from A to H. We don't have to visit the B first and then go from B to H because it would take more cost. And of course we are looking for the shortest path. Okay, so we consider B done. We don't have to bother it anymore. So in this situation we have 4 vertices on the heap: the D with minimum distance 20, node C with minimum distance 17, node H with minimum distance 8, and node E with minimum distance 9. We have to take the smallest one, which is the H, and we have to remove from the heap. And we have to consider all of its neighbors, the C and the F. We pose the question that, okay, what's smaller, 8 plus 7 or 17? Why 8 plus 7? Because in the previous steps we came to the conclusion that so far the shortest path is going to yield 8, so it takes 8 units to get from the node H, and it takes another 7 units to go from H to C. 15 is smaller than 17, so we update the minimum distance for vertex C as well as update the predecessor. C has the predecessor B, but because 15 is smaller than 17, we come to the conclusion that we come from H, so we update the predecessor accordingly. Okay, what about the F? We have to decide whether 8 plus 6 or infinity is the smaller one. Of course 14 is smaller, so we update it as well as the predecessor. The predecessor of F is going to be H. Okay, then the heap content will be D, C, F and E. E is the smallest one, so we keep visiting it and consider all of its neighbors. And we pose the same question: what's the smaller when we visit the node H? 9 plus 5, which is 14, or 8? Of course 8 is smaller, so it's good. What does it mean? It means that the shortest path so far from A to H is going directly from A to H. We don't have to visit E first and then go from E to H, because it would take more costs. Okay, then what about the node F? We have to consider whether 9 plus 4 is greater or 14. Of course 13 is greater, so we have to update the predecessor of F as well as the minimum distance of F. Then we have to consider the G. What's greater, 29 or infinity? Of course 29. And we consider all of its neighbors. The heap content is D, C, F and G. Of course we have to pick the smallest one. We can do it with the help of a heap. It's very important that heap data structure is very good for these kinds of problems. And we have to visit all of its neighbors. Have to decide whether 13 plus 1 is greater or 15. Of course 14 is smaller, so we have to update the min distance to C and we have to update the predecessors. We have to visit the G, so we have to decide whether 26 or 29 is greater. Of course 26, so we update the min distance for node G. And it's done. Then in the heap we have the D, the C and the node G. Of course the node C is the smallest one. We take out it from the heap, we visit all of its neighbors, we decide whether 17 is greater or the min distance for vertex D, which is 20. Of course 17 is smaller, so we update the min distance of vertex D and we update the predecessor as well. We visit the next neighbor of C, the node G, and we decide whether 25 is greater or 26. Of course 25, so we update it. We have 2 items in the heap now, the D with min distance 17 and the G with min distance 25. Of course D is the smallest one, so we keep visiting its neighbors. We decide whether 17 plus 9 is greater or 25. Of course 25, so nothing happens, we do not update. And of course the last item is G. It doesn't have any neighbors, so we terminate our algorithm and we come to the conclusion that with the help of the predecessor we are able to construct this shortest path tree. Why is it good? Because we just have to calculate it once and we can reuse it as many times as we want, but it's very important that if and only if the starting vertex haven't changed. So if we're starting from the A, okay, we can decide whether what's the shortest path from A to C. It takes 14 units and we have to go to E, then to F and then to C. What's the shortest path to G? It takes 25 units to get there from vertex A, and we have to go first to the vertex E, then from E to F, then from F to C, and then from C to G. So basically this is how Dijkstra's algorithm works. We are going to have a heap And as far as the heap is not empty, we are going to get the vertex with the smallest minimum distance. We are going to consider all of its neighbors, and if there's a better solution, then we are going to update the min distance and the predecessors for its neighbors, and we keep iterating as far as the heap is not empty. So that's all about Dijkstra's algorithm. Thanks for watching.